Today I'll be talking a little bit about an ultralight dark matter search using spatially separated quantum sensors like atomic clocks and cavities. Okay, so I think I can go over this stuff pretty quickly. So dark matter, we have extremely strong evidence for its existence, but we know very little or nothing about its microscopic composition. In particular, the array of candidates for what this dark matter particle could be is truly vast. In particular, it could have a mass range spanning something like 90 orders of magnitude. And so, we know it needs to be roughly above something like 10 to the negative 23 electron volts in the mass. Otherwise, the de Broglie wavelength would be too large for these dark matter candidates to essentially be bound in the smallest galaxies that we observe. If the dark matter is a fundamental particle, then presumably it has a mass below the Planck mass, although the dark matter particles could be macroscopic objects like primordial black holes or something like that. So there's a truly vast array of candidates for what this dark matter particles could be. And we don't really have a good idea of where in this parameter space they actually live. And so that makes the search for these candidates very difficult. Like this is a truly vast array of parameter space that we need to cover with experiments. And that poses several problems, of course. We can't design a single experiment that will be sensitive to all of these different kinds of dark matter particles. But there's also a cost, bottleneck involved in this. We can't spend millions of dollars on every one of these orders of magnitude. There's just too many. So it's really important then that we have a large number of different kinds of experiments in order to have access to the very large number of dark matter candidates that we have out there. And then as well, because of this cost, it's rather important that we also have relatively cheap experiments that we can use in order to have a large number of them so that we can cover such a wide space. Now, the best kind of cheap, of course, is free. And so that one of the things that I'll talk a little bit about is how to take advantage of existing precision experiments, right? If there are already experiments running for other purposes and we can repurpose that data, then that's a really good handle of casting as wide a net as possible. Now, you'll probably hear or you may know that so far the vast majority of the focus on dark matter detection so far has been on WIMPs. These are sort of weakly interacting massive particles, and there's some good reasons for that, but we have been searching for those WIMPs for a very long time and have not those have come up empty. So it's important to keep an open mind and have a look for these more broad candidates. And in particular, I'll be focusing on the complete other end of the spectrum on the ultralight side. So this is particles with mass well below the electron volt. And in this regime, we know that the dark matter particles would be bosonic. And this is because the total amount of dark matter in the universe is a constant. That's something that we can observe. So if the dark matter individual particle mass gets lighter and lighter, the number densities have to get higher and higher. And if the mass was below around an electron volt, these are number densities too large to be able to be explained by fermions. So in this region, we're looking for bosonic dark matter, and we'll talk a little bit more about that in a moment. Okay, and so just to zoom in on this problem just a little bit, this is the sort of canonical plot that you see over and over again for exclusions of dark matter candidates. This particular one is focused on WIMPs. So what this means is that the colored in regions are excluded by existing experiments. But we have to be a little bit mindful, essentially, when we look at a plot like this, that it's kind of hiding a bit of a secret. And that's what I was just talking about. So this plot really extends for something like 20 or more orders of magnitude to the right, as we go to heavier and heavier dark matter particle masses. This plot should also extend something like 20 or more orders of magnitude to the left for lighter and lighter dark matter candidates. And on the y-axis here is the cross-section, essentially the coupling strength of the dark matter. And really, this should extend kind of an infinite amount down for weaker and weaker couplings. So as you'll see in these plots, all of the exclusions get weaker and weaker as you go to larger and larger dark matter masses. Now, this is simply due to the number density. So as the dark matter particles get more and more heavy, the total mass of dark matter is the same, so the number of particles get less and less, and that just makes them harder to detect, particularly in these WIMP nuclear scattering type experiments. What I want to focus on is the other end. So you'll notice that there's a very sharp cutoff as we go to lower masses. And this is a sort of more fundamental problem, and this is just related to the energy of those dark matter particles. So we know that dark matter is bound within galaxies, which means it has roughly galactic velocities. This is a few hundred kilometers per second. And so if the dark matter particle gets lighter and lighter, the kinetic energy in those particles just gets less and less linearly with the mass. And in particular, the vast majority of these WIMP experiments are designed to search for nuclear recoils. And it's, roughly speaking, when the dark matter particle mass gets much less than the nuclear mass, there's simply not enough energy in those dark matter particles to cause a nuclear recoil that can be detected. So the challenge then is how to design experiments that can search for lighter and lighter dark matter particles. And one of the answers is to take advantage of atomic physics or atomic effects rather than the nuclear scattering that these experiments were initially designed to look for. So one of the ways to do that is to instead look for electron recoils. So this is dark matter particles which can scatter off atomic electrons rather than nuclei and cause observable ionizations. So I'm not going to talk much about that, but that's something that my PhD student, Ashley Cadell, has been working on a lot. So I think there's a paper a bit later on that you can have a look at. Now, of course, if you keep going lighter and lighter, you get the same problem again, a couple of orders of magnitude lower. If the mass drops much below that of the electron mass, you're also not going to get appreciable electron recoils. But in this regime, you can get for certain kinds of dark matter absorption. So this is something like the photoelectric effect for dark matter particles, which can also cause observable ionizations, which you can detect. But what I really want to focus on is the complete other end when the mass drops well below the electron volt level. In this case, the energy deposition will generally be too small to detect an individual scattering event. But instead, in this case, we can take advantage of the huge number density. So this is the region where we have bosonic dark matter. The number densities are so high that these particles will essentially act like a classical field. And so we can take advantage of these classical field-like nature of the dark matter particles to try and detect them using quantum sensing, in particular atomic clocks. So that's what I'll be talking about. Okay, so just to zoom in on that, so this is what we've said already, but as the dark matter mass gets lighter and lighter, the number density increases and increases, and you get these classical kind of effects. And there's a couple of regimes that will be of interest. The ones that I'll talk about is the most common case that you'll see is where there is no or very little self-interaction for the dark matter particles, in which case you will get a classically oscillating field. And this is a field that will oscillate at the Compton frequencies, so it's just the frequency set by the dark matter particle mass. And because this field has to have the energy density of the dark matter, then the square of this field is proportional to the known dark matter density in the galaxy. If there's some self-interactions, then you can also form some kind of macroscopic clumps of these dark matter particles. So I'll talk about that a little bit as well. And then I probably won't talk about, but you can also get local overdensities or constant builds up of these dark matter fields in certain particularly high gravity environments. Okay, so I talked about atomic clock. So let's just have a very brief introduction to what an atomic clock is. So what any clock is a frequency reference and then a method to count the clicks. And that's no different in an atomic clock. So in an atomic clock, the frequency reference is provided by an atomic transition. We can then compare that frequency to some external oscillator, for example, a laser. And if we can lock the frequency of that laser onto the frequency of this atomic transition, then we can use this, the oscillating external field, like the laser, for example, is now ticking as our clock, and we know that it's ticking at the right rate because it's locked onto the atomic transition frequency. And the key here is that atomic clocks have truly incredible accuracy. Parts, relative fractional frequency uncertainties of parts in 10 to the 18 or even less. So these are incredibly precise devices. So the idea is to use these incredibly precise sensors to search for dark matter. So the key is that if there's some kind of dark matter field, if this has any, even if it's very small interaction with standard model particles, then we expect those interactions that will have some impact on the atomic energy levels and therefore the atomic transition frequencies. So by monitoring the frequencies of atomic clocks, we hope to be able to see shifts in the atomic in the frequencies that are caused by interactions with these dark matter particles. So the idea is that you will have some kind of observable frequency shift in the clock, which will be dependent on the value of the dark matter field. Now I've written it here as though it's a linear coupling, but it could be quadratic or it could be much more complicated. But in general, this will depend on the value of the dark matter field. And it will also depend on some model-dependent parameter, which we refer to as sensitivity coefficients. So these are model-dependent, of course, and for a given model, these can be calculated, for example, from high-precision atomic structure theory. So this is given some model, we can calculate what the shift in atomic energy levels would be. Okay, so some common couplings that we will consider between a dark matter field and the regular standard model particles. So we can consider a coupling of the dark matter field to electromagnetism. So this gives rise to an effective variation in the fine structure constant. Similarly, coupling to the electron scalar currents can give rise to an apparent shift in the masses of fermions, like electrons and quarks. And also we can have coupling in the QCD sector, which gives rise to essentially a shift in the QCD energy scale. And particularly this can give rise to, for example, a shift in the apparent value of the proton mass, as well as changes in nuclear moments and nuclear charge radii. So if we have an optical atomic clock, so a transition between gross structure levels in an atom, this gives you sensitivity primarily to variations in the fine structure constant. If we have hyperfine clocks or microwave clocks, this gives rise to sensitivity to the fine structure constant, as well as differences between quark masses and electron masses. And if you have a cavity stabilized laser, this depends on the length of the cavity, which depends on the bore radius. So you also get sensitivity to electron mass and the fine structure constant. Okay, so one of the key signals that people typically look for is the case of an oscillating background field. So we talked about that just a moment ago. So this is the case to remind you where the dark matter field is oscillating at its Compton frequency, so set by its mass. And the change in frequency, which depends on the dark matter field, will therefore also oscillate at the Compton frequency, so set by the dark matter mass. And the amplitude of oscillations will depend on the amplitude of the field, as well as this sensitivity coefficient. So, for example, what you typically do then is compare the frequencies of two different atomic clocks. So, of course, you have to compare the frequencies of two atomic clocks so that you can have an observable to actually look for. And so here's an example of the coupling to electromagnetism. So this is the one that gives effective variation in the fine structure constant. And so from comparing different clocks, as long as they have different sensitivity to the fine structure constant, then you can have access to this decoupling. Similarly, if you have the comparison between one optical clock and one microwave clock, then you will also have access to this combination of the difference in the electron and proton masses, and this comes from the fact that the microwave transition also depends on the ratio of the electron to proton mass. But it's important to keep in mind that whenever you do this kind of experiment, couplings to dimensionful constants, so for example, to the electron mass on its own, will always cancel in these ratios. So you will only ever get access to differences in couplings to the quark and fermion masses. Now, this can be a problem in certain cases. For example, if you have universal couplings, or in general, we have no idea what individual couplings could be. So it would be useful to have experiments that have sensitivity to individual couplings on their own. So one way to do this in the regime of fast oscillations is to use something like one of these kind of experiments. So this is something that's been looked at a little bit. So I think Etienne will be giving a talk. I'm not sure if this is what he will be talking about, but there is a paper that he did on time delay interferometry. So this is looking at very fast oscillations that give you access to the coupling to the electron mass. So if that's what he's talking about, you can check out that talk or check out the talk regardless of what he's talking about. I'm sure it will be great. But what about slow oscillations in the other regime where these oscillations are very slow? So in a typical local experiment, you have a ratio of two atomic clock frequencies where those two atomic clocks are sitting next to each other or close to each other in a lab. And what that means is that both your clocks will be experiencing the same value of the dark matter field, and you will only see a signal if those two clocks have different sensitivities, different couplings to the dark matter field. And so it's in this difference that all certain couplings will always cancel or will always appear in particular combinations. On the other hand, if you take these two clocks and you put them very, very far apart, then the two clocks themselves will experience slightly different values for the dark matter field if it's oscillating. So that means that you can have a non-zero signal even if your two clocks have the exact same coupling to the dark matter because they are experiencing different local values of the dark matter field. Now, the oscillations of this dark matter field, the effective wavelength is very, very large. So on the one hand, that means that we can assume that these oscillations will be coherent along the terrestrial scales if we have clocks separated by kilometers or thousands of kilometers. The downside is that means the effective phase difference that you'll see, so this delta, which is the phase difference, the difference in the amplitude of the field at two different locations, will be very, very small. Very small, however, is a lot bigger than zero. So the fact that you get a non-zero signal is quite something from these sort of experiments. And in particular, what this does is allows you to have access to new couplings that simply don't show up in the other kinds of experiments. And so one of the things is you'll get two different contributions to a signal here. One is coming from the time-like separation of the two clocks. So essentially it takes some time to transmit the signal from one clock to the other, in which in that time the dark matter field will have oscillated a little bit. There's also a term that comes from the spatial separation of the clocks that is determined by the wavelength, the effective wavelength of the dark matter oscillations. And this is determined by the momentum of the field. And so one of the interesting things about the spatial separation term is that you end up actually getting a very large, well, a fractionally large daily modulation as the separation vector between the two clocks changes with respect to the average momentum of the dark matter particle, which is set by the motion of the Earth through the galactic halo. And the other important thing to notice from this is the signal, which will now scale with this phase shift, will scale with the size of the separation of the nodes in the network linearly. So whether that's with the time separation or the temporal or the spatial separation. So that means that if you have a large number of different nodes in the network, in the event that you do see a signal, there'll be a predicted scaling in signal size between different nodes in the network, which can help to distinguish between a real dark matter signal if one happens to be observed compared to, say, some spurious terrestrial source for the oscillations. So it's a nice handle for excluding non-dark matter sources in the signals. Okay, so we did an initial search using some existing data. So we used two data sources. One is from a comparison of cavity stabilized lasers across Europe. So this is 2,000 kilometers of fiber optic cable between PTB in Germany and NPL in the UK. And due to some sort of technical experimental details, this cavity comparison was sensitive to the spatial phase shift, whereas we also use data from the GPS satellites, which each have a rubidium microwave atomic clock on board. And these were sensitive to the temporal term. So even though the GPS clocks are much, much less sensitive than, or less accurate than the cavity stabilized lasers, the temporal term is typically a lot larger. So these were reasonably competitive. So what we've plotted here is the Fourier spectrum of the data. So if there was a dark matter signal, we would expect that to show up in this Fourier spectrum as a big spike. Now, of course, you do actually see many spikes in the GPS data. All of these spikes, it turns out, are at very regular intervals. So there's something one at like 15 minutes. There's one at sort of 6 hours, which is half of an orbit period. So these are almost certainly data processing or orbit artifacts from the GPS. Whereas in the cavities data, we didn't see any significant spikes. So what that means is that we can place constraints on dark matter models. So here are our constraints on any of the effective couplings to standard model fermions. So this is electrons and protons. And so one of the things that you can see is that even though we get this very large suppression from the spatially separated devices from this phase shift, the constraints are reasonably competitive. But that's not the main story. The main story is that all of the other constraints on this plot are actually on the difference between the coupling to the electron and proton mass. Our constraints, on the other hand, are sensitive only to the electron mass. So these are the first constraints on the DME coupling alone in this regime. The other interesting thing is that the spatial term, which is what we were looking for in the cavities analysis, you would expect to see a daily modulation in the dark matter signal if it were there. Now, we didn't see a dark matter signal, so that doesn't help in this case, but in the off chance that you do make a positive detection, looking for this daily modulation gives you another handle for distinguishing between a real and a not real effect. Okay, so I think I'll leave you there with my conclusion. These slides are available online for those who are interested, and otherwise I'll see you in the offline discussion.